So what you're going to do now in this exercise is actually practice this method of differentiating within the rules for differentiating. So there's three, I suppose, major rules, and they are that if you have a function of a function, then to differentiate it, then you basically differentiate the function using the method, and in this case it will be e to the x is e to the x, so you can see that we would differentiate using that new method because we've got the function in e. But function of a function says you also then must differentiate the little x function, and if it's ax plus b, differentiating that gives us an a, and you multiply by the derivative. So here it's got, so if you've got y is equal to some function in x, a little complication up there, then it is e to that function in x, then being multiplied by the derivative of that function with respect to x. Now that is usually using method 1, bring the index to the front and subtract 1 from the index. The other differentiating rule is the product rule. So this is the rule you must use when you recognize that you have the product of functions, two functions being multiplied. Now obviously in this exercise you're going to see that one of those functions will be a function with e to the x in it, and so that you can practice this new method for differentiating. And the other function might also be a different function, e to the x, or it may be a function that you've differentiated before, like x cubed plus 2x squared, something like that. The third differentiating rule that you must obey is the quotient rule. And the quotient rule says if you can see that you have u over v, where u is a function in x and v is a function in x, now one of those will involve e to the x, you must use this rule. Okay, I guess I'll do a couple of these, and then I'll leave some of them to do with you in class. But so d dx of e to the 2x, there's really only the one function here, so we don't have to worry quotient rule, we don't have to worry product rule. But just because this is more than simply x, we will use the function of the function rule. So like I'd said before, you'll see me do e to the 2x because when you differentiate it, it's itself. And rather than put times in by 2, I'll put multiply by 2 at the front. So 2e to the 2x, and we just leave it at that. With this next one, it is still, although we've got a coefficient, we'll still follow the rule. So it is minus 5e to the 2x. Now all that we need multiply by now is the derivative of the 2x. So it's multiplied by 2, which is negative 10e to the 2x. Maybe I'll leave that and do that one with you in class, but you probably wouldn't have any trouble. We saw again in properties of derivatives, if you have two functions being added, then you can just differentiate them as like an addition. So differentiating e to the x, you will get e to the x. Then differentiate e to the minus x. It's only slightly function of a function, isn't it? It'll be e to the minus x, but I'll have to multiply by the derivative of minus x, which is actually negative 1. and multiply. So, oh, that should be an e. So we would have e to the x minus e to the minus x. And we'd leave it at that. I think I'll leave 5 and do that one with you in class. Question 6. Now, this is function of a function. Yeah, quite a little bit complicated. So let's try and keep track of everything. So we've got the function to 4, and we have to differentiate this bracket to the 4th power. Now actually we do that exactly the same way as we did with our first method. So we're going to bring our 4 to the front, leave the bracket as it is, exactly, subtract 1 from the power. Then we go inside the bracket and we multiply by the derivative of inside. So we're going to multiply, and I can see that we're going to multiply by more than one thing. So I'm going to bracket. Now, the derivative of inside here is not just e to the 3x, but 3 times e to the 3x. Plus, now the derivative of 2x is just 2. If you need more explanation about that, then you can ask me, rewind it, rewind this video, ignore what I've got written there, try and do it yourself, see if you can get that answer. Yeah, that's one of the harder examples, I'd say. When we look at question 7, hopefully you see a product of functions. Oh, sorry. So it's asking you to differentiate x cubed, and there's a multiplication sign in there, times e to the x. Now they are two separate functions. X cubed is a function in x, e to the x is a separate function in x. They're being multiplied, so we must use the product rule. Now, not only when I was marking the HSC, but then again, and the feedback day in Sydney, the markers were saying that students who showed the working on the side here were more likely to get the correct answer. So with the product rule, so we know that the product rule is u v dash plus v u dash. And it doesn't matter what order we name the u and the v, but you probably would say u is equal to x cubed and v is equal to e to the x. So show the derivative u dash as 3x squared and show the derivative of v, which is v dash, as, well, if it was e to the x, then it's just simply e to the x. Now, the rule says you take u and you pair it with v dash. And again, I hadn't seen this before until I marked, but a lot of students actually for the product rule did this. So they literally joined their u and their v dash. So that then they wrote x cubed times e to the x. And then they put their plus and their other pair they joined, which was 3x squared, also times e to the x. Just looking at that and thinking about possible simplification, you may take out the e to the x. E to the x occurs in both, so that could be taken out as a common factor, leaving x cubed plus 3x squared, which of course cannot be simplified. So yes, I guess that is a simplified answer. With 8, hopefully it's obvious that it's a quotient or a fraction where we have a u and a v. U being the function on the top, v being the function on the bottom. And again, it was reinforced both when I marked and at the Marcus Feedback Day that the students that did their little calculations here on the side actually were more likely to get the correct answer. So students who showed u is equal to e to the 5x, therefore u dash is 5e to the 5x, and that v is equal to x and v dash is equal to 1. Now there's no little cross for this one because the pattern is quite different. I might actually transfer down to here. The pattern of the quotient rule is v u dash minus u v dash all on v squared. And again, it was really obvious to me that students who were writing this out and following that were more likely to get the right answer. Students who just looked at it on the formula sheet and thought that they could sub straight in here without writing it from the formula sheet into their solution were less likely to get it correct. So this doesn't take very much to write. It would take a matter of a few seconds, and it's written on the formula sheet for you anyway. So yes, please use it. V, what is V? V is x. U dash is 5e to the 5x. We're going to subtract u, which is e to the 5x times v dash is 1 all over v squared, and v is x, so it's x squared. E to the 5x is a common factor, and we're left with 5x minus 1 all on x squared. It didn't allow us to do any cancelling, but I guess that doesn't matter. It still looks neater and more simplified. And I'll leave question 9. It says simplify and then differentiate. So, yeah, you might like to try that anyway yourself. And but I will go through that one in class. So hopefully now you can try, like I said, exercise 2C. It was up to these before you hit the development questions. So maybe you'll be able to get through the questions up to and including 6B. And we'll talk about those on Thursday.